Alright guys, in this section we're going to be discussing optimization problems, and one of the most common applications of calculus involves the determination of minimum and maximum values, which is what we've been doing in the previous sections, especially in curve sketching. But now we're going to apply some of the same concepts to real applications. Consider how frequently you hear or read terms such as greatest profit, the least amount of cost, the least amount of time, optimum size, and so forth. All of these are going to be examples of optimization problems in the real world. So here are some guidelines for solving applied minimum and maximum problems. And we're going to start by identifying all given quantities and all quantities to be determined. If possible, make a sketch. That's always the recommendation here, guys. If there's a problem where you're not given or provided a picture or a sketch, it's always helpful to have a sketch at hand. Number 2, write a primary equation for the quantity that is to be maximized or minimized. This could be a geometric formula or some formula that is given by the problem. Number 3, reduce the primary equation to one having a single independent variable, and we'll see how to do that. This may involve the use of a secondary equation, which we're going to solve for one variable and substitute it into the next one, as we'll see in some examples. And then we're going to determine the feasible domain of the primary equation, that is to determine the values for which the stated problem makes sense. And finally, we're going to determine the desired maximum and minimum value by the calculus techniques that we've been practicing. Okay, so here's an example. We have the sum of the first number and twice the second number is 108, and the product is a maximum. Okay, here we want to find two numbers. We want to find two numbers where this conditions apply. The sum of the first number and twice the second number is 108, and the product is a maximum. So the first thing we want to do from the guidelines is identify all the quantities that are given and everything that is to be determined. So I'm going to label my numbers as x and y. So I'm going to say x is my first number, y is my second number, and I use what the statement says to express an equation. So the sum of the first number, x for us, plus twice the second number, so 2y, is equal to 108. All right, so this is what's given by the problem. Now next, it also says that the product, x times y, is going to be a maximum. So in order to have an equation, I'm going to call this product P, so that I know that the product is equal to x times y, because I just take the two numbers and multiply them together. I don't know what x and y are, but that's what we're going to find in this problem. And this P equal to xy will be my primary equation, since I'm going to maximize this product. Now, following the guidelines here, I need to write P in terms of just one variable, either x or y, it doesn't matter. So for that, I'm going to use the secondary equation. So this first equation that I have here in the problem, the one that was given by the problem, x plus 2y equal to 108, becomes my secondary equation. And I'm going to solve for x. Again, you can choose to solve for y if you like, but I'm going to choose x here. This is pretty straightforward. And solve it in terms of y, and use that to substitute x into my primary equation. So instead of x, I'm going to write 108 minus 2y, and all that multiplied times y is going to be equal to 108y minus 2y squared. Notice how I've accomplished step number 3. I have my product in terms of just one variable, in this case y, with the purpose of having a function of one of the variables. That way I can take the derivative with respect of that variable. In this case is y for us. So we go ahead and do that. The derivative of the product with respect to y is going to be equal to 108 minus 4y. Okay, now here's where the calculus comes in. Since this product is going to be a maximum, then let's find where that maximum happens. And we do that by setting the derivative equal to 0 to find the critical points. And this is a pretty straightforward equation. If you set the derivative equal to 0, you get that y is equal to 27. In this particular problem, we only get this one critical point, so this one has to be our max. Now you can check this using one of the tests that we've done in the previous section, either the first derivative test or the second derivative test. But this product function is going to have a maximum at y equal to 27. From there, I can figure out what x is, and x is going to be equal to 108 minus 2 times 27, since I already have y, and that's equal to 54. Therefore, we're going to have that the product is a maximum. In other words, x times y, or the product of the two numbers, is going to be a maximum when the first number is equal to 54 and the second number is equal to 27. And there we have it. All right, here we have another example. We find the length and width of a rectangle that has an area of 49 square feet and a minimum perimeter. So notice how automatically, just by reading the question here, we kind of see two equations going on here, one for area and one for perimeter. Your job is to identify which one is your primary one. In other words, which one is the one that you're going to take the derivative of. And you identify that by reading the problem, seeing which one you require. In this case, we want to find the minimum, or we want a minimum perimeter. So therefore, the perimeter formula is the one that we're going to take the derivative of. Okay, we start by setting up a sketch here, since it applies. And we have the length is x and the width I'm going to label as y, right? The area is the product, length times width, so that's x times y equal to 49 given by the problem. And I go ahead and solve for y, which you could also do x, but I'm just choosing y here to be equal to 49 over x, since I'm going to have to substitute it into my primary equation to get the perimeter in terms of one variable, in this case x. Doing that, 2x plus 2y, we substitute y for 49 over x, and we get 2x plus 98 over x. Now we're ready to take the derivative. Since this perimeter is a minimum, we find the derivative of the perimeter with respect to x, and that is 2 minus 98 over x squared. And we want to see when this is equal to 0. Doing a little bit of algebra and combining the 2 minus 98 over x squared, I'm going to get 2x squared minus 98 over x squared. All of that equal to 0. And since a fraction is only equal to 0 when the top is equal to 0, then we only care about the numerator being equal to 0. 2x squared minus 98 equal to 0. We get the x squared is equal to 49. Then x is equal to plus or minus 7. But since we're talking about lengths here, length and width and positive amounts, we only care about the 7. Now, we can use our first derivative test or our second derivative test to actually show that there is a minimum here. So again, you use any of the tests to show that. I'll use actually the second derivative test to show that we have a minimum at x equal to 7. We first have to find the second derivative, and I already have my first derivative. So the second derivative is going to be equal to derivative of 2 is just 0, and derivative of 98 over x squared is going to be, it has a negative in front, but when you do the derivative, it has bring a negative 2 to the front. So then those negatives cancel out, so it comes out to be 196 over x cubed. And that second derivative is actually greater than 0 when x is 7. So if you plug in 7 in there, we don't really care about the number, we just know it's positive. And by second derivative test, we know that there is a relative minimum at x equal to 7. So again, that's just to confirm that we actually have a minimum at x equal to 7. So we have one of the dimensions. So to find y, we just we substitute our x in our equation above. So y is going to be equal to 49 over 7, which is also 7. All right, so you can see how the perimeter is going to be a minimum when the rectangle has dimensions 7 feet. So it's in fact a square. The rectangle is actually a square. Okay, here's another example. We have a rectangle poster is to contain 648 square inches of print. The margins at the top and bottom of the poster are to be 2 inches, and the margins on the left and right are to be 1 inch. What should the dimensions of the poster be so that the least amount of poster is used? All right. So first of all, we want to get a sketch going here, just to kind of have a visual of what we're talking about. So here we have it. We have a poster there, so pretend the larger square or the larger rectangle is the poster, and the inner one is the amount, is where the writing is going to go, right? Where the print is going to go. So I'm going to label the dimensions of the printed area as x times x by y. So dimensions x, width, length y. And for the poster, we're going to have, since the top and bottom margin is 2 inches, I'm going to add 2 inches to top and bottom to that y, the side label as y. So that side of the poster is going to be y plus 4. In the same way, the top side of the side on the top of the poster is going to be x plus 2, since you're adding 1 inch to the left and 1 inch to the right of the poster there. Now, using the information that we have from the problem, we have the product, which is the area where the print is going to go. It's going to be x times y. So that's equal to 648 given by the problem. I solve for y because I'm going to have to substitute that into my primary equation, which is the area of the poster, right? So the area of poster is x plus 2 times y plus 4. I multiply that out. Notice how I substitute y for 648 divided by x. I'm going to FOIL those two binomials, and I get 648 plus 1296 over x plus 4x plus 8. Okay, cleaning it up a little bit, we get 4x plus 1296 x to the negative 1 plus 656. Now we're ready to take the derivative. The derivative of the area there of the whole poster with respect to x is going to be equal to 4 minus 1296 x to the negative 2, which is the same thing as 4 minus 1296 over x squared. Setting that equal to 0, we're going to find our critical numbers. And again, just like we've done before, we combine those two things. We only care when the top is equal to 0. So that's 4x squared minus 1296. Solving for x, or x squared, is equal to 324. Then x is the square root of 324, which is 18. Again, we only care about the positive since we're talking about positive quantities here. If x is equal to 18, then y will be equal to 648 divided by 18, and that's equal to 36. Again, you can verify that the area function a is in fact a minimum at x equal to 18 by using your first derivative test or second derivative test. Therefore, the dimensions of the poster are going to be, now remember the poster was x plus 2 by y plus 4. So x 18, I add 2, so that gives me 20 inches by y plus 4. Y was 36, plus 4 is 40 inches. It's 20 by 40. Here we have one more example. We have a farmer plans to fence a rectangular pasture adjacent to a river. The pasture must contain 405,000 square meters in order to provide enough grass for the herd. No fencing needed along the river. What dimensions will require the least amount of fencing? Okay, this is a very typical problem, very practical. So let's get a sketch going here. Pretend we're going to fence a rectangular area, and here on the top I have a river. So I'm not going to fence the side of the river there. I'm not leave that open. So I just have a side x and two sides labeled as y here. And again, given by the problem, the area must contain 405,000 square meters. So my product, x times y, of the dimensions of the rectangle has to be equal to 405,000. Right? Solving for y. Again, you can do this for x. It doesn't matter which variable you solve for. You just got to be able to solve for one, so you can substitute that into your primary equation. Now, since we want to minimize the amount of fencing, I'm going to call my primary equation is f. F is going to be equal to the perimeter, or to the sum of all those sides of fencing. In this case, 1x plus 2y, and I'm going to substitute my y from my secondary equation above, and I get x plus 2 times 405,000 over x. Now with that, I'm ready to take the derivative of this function with respect to x, and that's going to be equal to 1 minus 810,000 over x squared. Now setting this equal to 0 to figure out my critical numbers and ultimately the minimum, we get that x squared minus 810,000 is equal to 0. Again, combining the two terms, getting the numerator equal to 0, I get that x squared is equal to 810,000. Let's take the square root of that, and x is equal to plus or minus 900. But then again, we're only interested in the positive amount since we're talking about distances here, or lengths. If x is 900, then y is going to be equal to 405,000 divided by 900, which is equal to 450. Now again, just like the other problems, you can verify that this function f actually has a minimum at x equal to 900 with your first derivative test or your second derivative test. And just for the sake of time, I'm skipping that step, and we get that the dimension of the fence, in order to have the least amount of fencing, the dimensions have to be 900 meters by 450 meters. There we have it.